Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
Thank you very much for joining us. Today is our webinar topic on high-speed design. I think you'll find it to be a very fascinating 1 hour of information over here. All right, so my two objectives over here is, number one, to cover high-speed design rules. And I mean, we're going to definitely go into some details about this, but these are ones what I'll call the category of high-speed design rules. And then I'm briefly going to cover some of the new functions on Altium Designer 15. So if I was to put a percentage on this, about 85% of that is going to be on talking about the high-speed rules themselves, because the rules are almost useless if you don't understand what the numbers are that you got to put into them. And then we're also going to cover this, probably say about 15% of the time. So that's why I said if you're not necessarily an Altium user, you're still going to get a tremendous value out of this webinar today. And if you are an Altium user and you're looking to get more information about any type of the rules, please do check out the webinar we did about a year ago. It's very applicable to what you see now. There are a few new features that will look slightly different, but all those features from back then still exist in the tool today. All right. High-speed design rule category. There are 6 rules in here. By default, each and every single one of those particular rules in this category are disabled. So that when you open up a new PCB dock, that's what you're going to get. So you've got to enable those rules. And I'm going to go through each one of these rules at length. In terms of the category itself, it's really hard to put a general category to any one of these rules, because if you really look at it, each one of these rules has a different impact on different aspects of the printed circuit board. For example, the maximum via count, why do we care? Why is that even a high-speed design rule? Yes, there is an impact on your design when you have a certain number of vias or how they are being used, but it's really actually more of a manufacturing rule more than anything else. So, especially the vias under the SMD, which is the surface mount device, that one is a huge one. It has a huge impact on fabrication just as much as it has an impact on high speed. So what you're going to see over here is that it's really hard for Altium to categorize these things because you don't really have a one-size-fits-all. These things have different things. As a matter of fact, when it gets to routing, one of the most important rules in high-speed design is the width rule, right? And we know that the width plays a huge part in the impedances, which plays a huge part in the high-speed design. And that's not even under the high-speed category, it's under the routing category. So just bear in mind that I'd say about half of the rules in Altium, above and beyond high-speed design, or what they call categorized as high-speed design, actually have an impact on your signals and on your entire board. All right, and one other thing I'm going to do is I am going to go down this list over here, but I am going to actually talk about the length first, because if we understand the length, the parallel segment aspect comes into better view. All right, so what's the rule? It's simple enough. If you turn it on, they're going to say, well, what's the minimum length and what's the maximum length? And it works rather nicely. So if I escape out of this for a moment, we can take a look at this over here. And I'll page up so you can see this a little bit easier. So I've created this here, and what I've done, and I'm going to use this, this tool here called the PCB Rules and Violations panel. I don't believe I talked about it in the last webinar when I did this. It's a very, very useful panel because you can see the rules up front anytime you need to, where in the past, before they had this, and I think this has been in for the last couple of versions, but in the earlier days of Altium, they didn't have this, and you would have had to always go to Design Rules, and take a look at the rules. And of course, if you open up this dialog over here, it locks everything else out. Whereas a panel allows you to see things, but it allows you to go quickly back into the editor as you're doing that, which is very useful. And another mention over here is that with this particular panel, it's not a part of what you call the PCB panel. That's a separate panel, and I know they stack a lot of sub-panels onto the PCB panel, like the X signals, which they just added. But the PCB rules and violations is its own panel, which is very useful, and they list all the rules over here. So if I want to see what this rule is all about, again, I could go into design rules, but instead what I'm going to do over here is I'm going to look for the length rule. So here's the length rule here, and I actually have two rules set up. Okay? And if I click on this one over here, because I set up a very specific net class for this, these all three got highlighted over here. So I can see the rule, and if I have any violations, it will show me where the rule is. Now for this particular rule, and by the way, what's also nice about this, I can double click into this, and it shows me what the violation is. If I right click on it, I can also rerun the rule if I've changed it over here as well. And I believe if I double click on this one down here, I can actually go in there and modify the rule. So in this example here, I created this thing called net class, and I'll talk about that for a few moments. But what I've got over here is I got a minimum and I've got a maximum. So I set this up saying, well, I want my minimum to be 250 mils and my maximum to be 500 mils. And so the way I set this up just to demonstrate it over here is I do have two violations, because this example on the top over here is less than 250, so it violates it and it flags it as such. And then up over here, it's saying that actually this is, I don't have my dimension right over here, it's saying it's 520, but it's still over the 500 mil limit that I set up. So the rule itself is easy enough to understand. One other thing I'm just going to mention, because I don't think I went into a lot of detail about this in the last rule set over here. What I did here was I actually created all my rules in my schematics. Now I can easily create them on the PCB side. It's simple enough. If I go, oops, push it here, and let's click on this. If I go over here to design and I go to classes, all right, I can create classes very easily with any type of net. I can just right click over here, I can add a class in, and here are all my nets, and I just simply add them in there, and boom, I've got a class. So on the PCB side, it's easy enough to do. In this case here, I actually created the classes on the schematic side, and you can create classes through things called directives, and this is an example of one right here. So I actually created this class, and as long as I either put this little directive on each one of these lengths, or if I put a blanket around this and put it on top of the blanket, anything within the blanket will fall under this class, at least the net class will. These are components, and components are handled through the properties. If I want a component property, I've got to put it in the parameters. But the point I'm trying to make over here is that if you're trying to create a class, it's easy enough to do on this end. So you may be asking where you find these. Well, if you go into design, pardon me, actually, you want to go into place. And if you go into place and you go into directives, you'll find the blanket over here. So you draw it out like a box. And then you can put over here your net class, and you place that on top, and away you go. Once you've saved this and compiled this, you basically will push this over to the PCB side. Right? And then once on the PCB side, the net class already exists. It's now just a matter of creating a rule from that. That's what I want to say about that. Now let's get into the nitty-gritty over here, because you're saying, all right, I kind of understand where you're going with the rules. It's nice that you can set a min-max for a length. How is this useful to me? And that's where we want to spend some time. So let me jump back over here to my current slide. Okay. What are we using it for? Well, the big thing I think most of us use it for is the concept of propagation delay. We want to make sure that when we're going from point A to point B, that we know that we're going to get there in the nick of time. And by the way, you're going to see some equations a little bit later on that actually address this much further. Okay? And at that point, we'll also talk about, we want to talk about a little bit about match lengthing. Actually, let me reset over here. I'm going to talk about current loops first and foremost. And I think we got to spend a lot of time in this. Say a couple of minutes. The reason I want to talk about current loops is because they play a major factor in high-speed design. Propagation, I think all of us understand. Propagation is a situation where we got to go from point A to point B. The equations I'm going to show you a little bit later on basically allow you to go from a frequency to a length. And you're going to you'll need that, because a lot of times this thing's looking for numbers, and you've got to take, well, how do I get a number on this? Sometimes you can look at the spec sheets to get that. Other times it's just based on some math that you got to do in order to figure out, well, the distance I need is X because of this situation or because of this frequency. The next one is, or for purposes, is this thing called match length. And I say to a certain extent because Altium has a very specific rule for match length. And then, of course, the last thing is for the tuning of stubs and antennas. So you're going to see a couple times I'm going to refer back to this, but just always remember this. Then an antenna is defined by its distance or its length and its frequency. Okay? But let's take a look at the current loops here for a few minutes. I want to go back to some of the fundamentals, and you'll see why here in just a minute. Where there's a voltage, there's a current, and vice versa. There's a little A over here. And the reason I bring this up is that sometimes we get so caught up in a capacitive field or an inductive field that we forget that there still is a voltage even though you're dealing with an inductor, and there's still a current when you're dealing with a capacitor. So they're always there together. You don't separate them. And that voltages do create E fields. Again, they happen to, every time you deal with a capacitor, you're always dealing with the E field effect more so than the H field effect, and vice versa. When you're dealing with inductors, you're dealing more with the magnetic effects than you are with the electrical effects. The fact of the matter is, therefore, is that every time you propagate a signal from point A to point B, you have an electromagnetic field. Every single signal. It's really amazing. Okay, we're not talking just about gigahertz signals. We're also talking about a 1 hertz signal also has this as well. Granted, it's much more dissipated, right, because it's much slower. The energy is much slower, but it still exists. And up to this point, or when I first started in the industry, especially being a logic guy for the first 10 years of my career, I never worried about this because it wasn't playing a huge role in it. With high-speed design, I really have to understand that pretty much every one of my signals is going to radiate. And that's my next slide over here. All signals radiate just by the mere fact we push current, which is a bunch of electrons from point A to point B. So what's really the major purpose of high-speed design is to mitigate the radiation, right? Well, here's another thing, too, we got to remember. I think we forget, too, but you probably remember in your old science days, probably 6th grade, 5th grade science, when you first started to talk about electricity, you had a battery. And in the battery, you had a light bulb. And if you completed the circuit, the light bulb turned on. And if you pulled away the wire, it turned off. And sometimes we forget that every signal really does have a closed loop. And this is very true in the logic area. When I was doing logic design, I was worried about what I'll call the gazintas and the gazadas. I was worried about, look, I've got this thing going from point A to point B, and I got to make sure it goes there in the appropriate amount of time. Well, in high-speed design, that's only half the story. In high-speed design, it's not only going from point A, but it's going to point B to point A simultaneously. And here's a really great representation of this going on over here, where you have two signals, and if you can imagine them coming out of the screen towards you, you've got an E field and an electromagnetic field. So when you send something, it's going to also return, and you're going to get these field effects that you're seeing over here. Now, because of this, we really have to understand this concept of a closed loop a little bit better. And there's a really phenomenal experiment that they've done. This is a computer simulation that was done by a fellow by the name of Marco Klinger, and I thought it was very worthwhile to post it over here. Howard Johnson's book, I think, also makes reference to this thing as well. But what we're dealing with here is energy transfer. And now it's obvious on all frequencies we're dealing with energy transfer, but in high-speed design, we're dealing with an amazing amount of transfer in a very short period of time. We always have to go back to the laws of physics, the conservation of energy. Energy is neither destroyed nor created. So when we go from point A to point B, energy just does not go away. It still exists. So what happens to that energy once it hits point B? And that's what this experiment is showing. So what they're doing over here, so this is not a printed circuit board. This is actually a rather large board. So if you imagine everything here being conductive, the whole plate is conductive. You have a wire over here which is conductive. It's floating about 2 centimeters above, well, this computer simulation, so it's exactly 2 centimeters above. And they are energizing this with a 1-volt AC, a variable AC. So they're going to change the AC over here, AC voltage, to different frequencies. And what they're going to do is look for the current density on this plate over here. So let's take a look at the results. I don't want to just throw the whole slide out and show all the results because I want you to kind of think through this. So at 10 hertz and 100 hertz, it all looks the same. And here is the effect. Again, this is current density, where the dark blue means that there's little to no current, very little currents being detected, where the green means that there's a lot of current being detected. And then as you get to light green and some semi-blue, you're talking about current density between it. So they also drew in these lines. So these lines over here are just drawn in for reference points. This point over here is where it enters into the board after the line has been hovering above for 2 centimeters. And this is where we're actually energizing with our AC voltage. So we go from all the way up here, and then we energize the circuit. It's going through the line over here. It's going back down to the board. And the question is, how is it returning back to point A? Now, in 10 hertz, it looks kind of as if it's following a field based on the hypotenuse. And at 100 hertz, it also looks like it's following this field as well. Now, being a logic guy, again, for the first 10 years I did logic, and also just remembering my geometry, saying, well, the hypotenuse is always the shortest point between two legs. The two legs can either be equal to the hypotenuse or less, but they can't be more than the hypotenuse. So I'm thinking, again, going through my old circuit days, saying, well, the current always wants to take the path of least resistance. So therefore, I could logically conclude that from point B to point A, it's going to follow the hypotenuse. Okay? Well, guess what? I'm dead wrong. Okay? It's not following the hypotenuse. And what happens at even 1 kilohertz is you already start seeing the effect over here of the electromagnetic, the effects of the electromagnetic forces. You go from point A over here to point B. Well, again, there has to be a closed loop over here. So the minute it goes back into the plane, it starts following back the path it took back to point A. That's a huge finding over here. And as you go higher and higher in frequency, it pulls itself below, almost directly below where that wire is. And at 1 gigahertz, it's directly below it. So in high-speed design, therefore, we have to remember, A, we're dealing with a closed loop, and B, we better have some type of material underneath this, something that it can conduct itself and travel back on. Otherwise, it's going to try to find its way back to point A. The question is, are you going to give it an easy path to go by, or is it going to be banging around and creating a tremendous amount of noise in order to get back to point A? Regardless, it's going to get back to point A. So we've got to be able to control that. And that's why this is really, really important that we understand the length of these things and that the fact that we do have this closed loop over here. Okay. So going back to our rule here, to summarize this rule, to really minimize radiation, we do want to keep the length short. And if you have to say, hey, look, I really want to try to keep it within a certain distance, you certainly can do this with this rule. And we always have to remember, especially us logic guys who come from the old school, we're not only going from point A to point B, but we're going back from point B to point A. And to minimize the propagation delay again, so in digital, we just got to keep that length short. And of course, I also want to remind people too that for antennas, you basically put out a stub, and from that stub over there, again, if you have a frequency and you have a distance, you get an antenna or a receiver for a signal. And then, of course, you need to have a minimum and maximum in order to make sure that you actually pick up the frequency that you desire on that. So that's the first rule over here. So let's click on the parallel segment rule. And this is where we're going to spend a good deal of time because this one's really, really important. Because what are we dealing with half the time? Yes, current loops we can control rather easily as long as we're smart about how we design it. But having stuff bleed onto other stuff, or what we call the aggressor-victim stuff, yeah, it gets a little trickier. Okay? So we're dealing with crosstalk or aggressor-victim issues, and I am going to call the aggressor or the victim so we can have a relationship between these two signals. And we're also dealing with something that's called the antenna quarter wavelength issues. This is kind of an interesting area because if you go to the literature on the internet, what I have found more often than not that people have disregarded this aspect of it. And it shouldn't be disregarded because, as you're going to see, there still can be an opportunity for an antenna even if there's only one signal propagating on that line. And it may not be a consistent signal. I think we always think that this thing is constantly bouncing up and down, and therefore this thing is constantly radiating. But it only takes one signal to basically have a crosstalk event. So for the rule itself, they allow you a couple of things here. But the layer checking can be either done on the same layer, or you can do a drop down here and you can say different layers. And I'll talk a lot more about that here in just a minute because doing things on different layers has a monumental impact on stuff. What's also interesting about this is that this is an if-then statement. So for a parallel gap of 10 mils or less, the parallel limit is set to a certain distance. Okay? So it's not like you're saying, I want a parallel gap of this and I want a length of this. You're saying, no, for this gap, this is the limit. Okay? Let's talk about signals on different layers. All right. The problem with signals being on different layers is that there are too many scenarios and factors to come up with any type of decent rule of thumb on this. Okay? And here's an example of one. So if we say different layers, let's assume that this was your layer 1 and this is your layer 2, and you just happen to have a plane on layer 3. Now, some of you have already recognized this is probably not the best way to be designing high speed, but bear with me here for a moment, because for those people who are learning these things, this is going to play a big role in how you set these layers up. So we've got T1 and T2. So we now have a number of different scenarios we've got to deal with. First and foremost, let's talk about T2 over here. If T2 is the aggressor, then how does it impact T1? Well, actually, what you're going to see is there's something called a mutual inductance. And what do we mean by a mutual coupling? Pardon me. The mutual coupling is when you have both a capacitative effect and an inductive effect. And so how much of, and what T2 is going to do is it's going to actually influence what's possibly going on T1, depending on the length of this over here. There's other factors as well. But how T2 influences T1 and how T1 will influence T2 are different. Okay? The reason why, for example, T2 will be different is because T2 over here, its magnetic fields actually get smushed out because their magnetic fields cannot wrap itself around the plane over here. So these fields get kind of mushed out, but the electric field is still the same, or is still as strong as if it was between T2 and T1. So because of that, it's really hard to come up with an all-defining rule as to how you'd handle T1 or how you'd handle T2. Now, T1 is the one that's being the aggressor. It doesn't feel the influence of the plane as much. But it gets more trickier than this. Even if that explanation is being very high level and you're not really sure about how these waves are interacting with each other, we have a lot of issues with just the physical layout of this. So first and foremost, we're dealing with different layer heights. So how do you set up a rule when you have different layer heights? Because if there's different layer heights, you have different basically different rules to deal with, because that distance plays a major role between these two. The electromagnetic fields between the two are going to be impacted by its distance. It's also different dielectrics. So if there's a different dielectric on top of T1 versus the prepreg that may be between T1 and T2, that's going to play a huge role in how the fields are going to affect each other. There's also different trace thicknesses. You'll notice I drew these like this. These could possibly be upside down. You got to keep in mind that it's a subtractive process when they are etching out these boards in the fabrication process. So they never look square. They always look trapezoidal depending on how they etch this out. So you can see this example over here. So they might be trapezoidal in the other way, but now the geometries are getting all changed. And by the way, they may not even be straight lines. They could be curves. So now the geometries are getting very, very unusual. And there's another factor over here, too. And you'll notice I purposely drew these things off a little bit. You have the registering of layers. And the registering of layers is always problematic, even for FR4 material, which is the classic material. What happens is that you got to keep in mind that each one of these layers, you take something that's called a core. It's got copper on the top, copper on the bottom, and you etch out the copper on the top, and you etch out the copper on the bottom. And if this is a 4-layer board, then you've done that now to layer 1 and layer 2. Now you've got to do the same thing for layer 3 and layer 4. And then later on, you're going to put this stuff called prepreg between the two, and you're going to heat them up so that they laminate to each other. Okay? Well, now you've got a registration issue, because are you going to get them exactly on top of each other? In some cases, there's going to be expansion. And some of the new materials, they may have lower dielectric constants, which you want high-speed design, but they have a tremendous impact on the way you can manufacturing stuff. There's one example I was given, and I forgot the name of the material. Someone wanted to use 8 layers of it because its dielectric constant was phenomenally low. They said, this is great stuff. So they went off and they did this layer stack on their own. And then they went to the fabricator and said, make this for them. And they quickly found out that they couldn't make it because this material is only good for maybe 4 layers at most, and the registrations wouldn't work. So just bear in mind that even with known processes like FR4, this stuff could travel away from each other. So the short of it is it becomes extremely difficult for us to come up with any decent rule of thumb or any decent rule without using a field solver if we're going to run parallel lines on different layers. So, well, what can we do here? Well, the best practices, generally speaking, again, because of that closed current loop that we've got to remind ourselves of, is that we should always have a piece of copper that we can reference. For every signal plane, there should be some type of reference. For every signal, we should have a reference plane to it. And so we should never really even have what we had on the prior slide of two signal layers without some type of reference to a ground plane. And yeah, you can pour a polygon pore on the top, in Altium so that you can flood it with copper and reduce some of the noise, but that's no guarantee that you're going to have a clean current loop to return to. If you are working for Dell, I know that for a fact that I think based on the literature I've read, they don't want to put this extra layer in here. It's to save on cost. But if you're going to do something like that, or if you really understand this, then you can actually run these things parallel to each other. And yes, there'll be a small area that might couple to each other. However, because the magnetic fields are running parallel with the line trace over here, yes, there's still going to be an electric field effect on this, but it's going to be really, really minimal. Not enough to cause a lot of problems. So you can, if you're doing two signals without a reference plane and you feel comfortable enough about doing that, then you can run these things parallel. But you better make sure that you organize this in such a way that you don't ever get into a situation where you have both of these things running parallel to each other, or you're going to have a lot of problems with it. All right, let me jump on over here to parallel traces on the same layer, which is more common. Far more predictable because now we're dealing with the same dielectric constant. We're dealing with the same references of the plane. And by the way, these aren't sitting on the plane. They're floating above it. So they're not shorted to them. But the fact I'm trying to remains over here is the same rules apply for either trace. Generally speaking, I wish I could go into a little more detail on this, but I'm going to keep this really brief. You can always look this up. If the aggressor has both inductive and capacitive coupling, and when you have an inductive coupling, you're basically changing the voltage, and when you've got capacitive voltage, you have a change of current. And both of these obviously are happening somewhat at the same time. One may happen before the other, depending on the circumstances that you've got. But the fact of the matter is that there's an impedance here that converts between the current and the voltage and the victim. And so now we've got to start dealing with this. Well, how do we deal with it? Well, excuse me, the impedance plays a huge role in what's called the trace and space rule. And it's really important that when you're doing high-speed design, I think we've emphasized this a number of times, we can't I think, emphasize it enough, that when you're starting a high-speed design, you need to go to your fabricator right at the beginning of the whole process and say, this is how many layers I'm going to use. These are the impedances I need to adhere to. I'm doing a USB bus, or I'm doing a DDR3 bus, or I've got a classic 50 ohm line between point A and point B, and they're going to take that information, they're going to take your layer stack stuff, they're going to find which dielectrics they're going to use, which basically are the materials that are going to best handle that, and they're going to come back to you and say, this is your trace width, and this is your spacing that you need to leave in order for these impedances to work. By the way, down here, you're seeing the ICD stack-up planner. This is a tool that Altium sells. We don't sell it, but Altium does sell it. And it's kind of a slick tool. It's a dangerous tool if you don't know how to do these things. But if you're just trying to get a better understanding of how you get the trace width and the trace width and the trace space, this is a great tool to take a look at it because it provides all the different dielectric constants based on different materials, whether it's the core, the pre-preg, or the solder mask. So it's a pretty slick tool to have. But again, if you're not familiar with this and you're new to high-speed design, make sure that you work with your fabrication house to make sure that what you're coming up with is even manufacturable. Impedance is, again, based on width, thickness, and dielectric constant. So as a result of this, we remember back at the original rule, it's an if-then rule. It's saying, well, what is this distance that we have to be careful of before we really need to understand a distance where we're going to start injecting a lot of noise on top of each other? Well, the trace and space rule will give us that minimum clearance. And of course, the further away you keep those two from each other, the better off it is. But we still need to know at what point there's going to be an influence of the aggressor onto the victim. And this is where it gets a little more trickier. So bear with me as I get through this here. At short lengths, the effect is really minimal. And of course, at long lengths, the signal, if you run them long enough, you'll basically get the signal of the aggressor onto the victim. So you'll actually get a phantom signal onto the victim over there. So therefore, we need to know this concept of a critical length. All right. So in order to figure this out, we need to understand this length. And obviously, we have a frequency that's involved with the signal. Well, as I mentioned earlier on, what's an antenna? It's something that's based on frequency and length. So the question is there a frequency on our aggressor signal that's going to cause what we call an accidental antenna? Why is it called accidental? Because we didn't want the antenna. Okay? So if we go over, so let's just recall for a moment a digital signal. So everything I'm going to talk about now is primarily for the digital domain. Okay? So in a digital signal, we're talking about a synthetic signal. What do we mean by a synthetic signal? It's because the rising edge and the falling edge are made of different frequencies. Synthetic signals mean that they're man-made, that it's something that we create, as opposed to something in nature where a sine wave would be something that's very natural. We hear it in tones, we hear it in audio all the time, right? And as opposed to a digital signal where it's going up and down. And it's trying to do it in a sharp line altogether. And what you've got over there in this synthetic signal is a summation of different frequencies, many of which are actually in the hundreds or gigahertz range. So even if the signal is occasional, and this is the key thing, even if you're just sending this signal once in a while, it doesn't have to be constant. There doesn't have to be a frequency or a synchronization to anything else. It just has to be a signal that's going from point A to point B. Even if it's occasional, it still creates an antenna. So then, if we can determine what this frequency that could cause this, then we need to model the rising time or the falling edges to do this, to determine the frequency. If we determine the frequency through some of the equations we're going to show you over here in a moment, then you can actually also determine what that distance is going to be before you actually start getting possible quarter wave effects on your between a victim and aggressor. So for this presentation, I just want to emphasize this, that this is not the way, it is one of many ways of doing this. But what we're going to do is we're going to model the rise time using the sine wave, because this will give us, if we understand this model, the idea behind this is if we have a sine wave and we can model it to the rising edge, or even the falling edge if you want to do it that way, but the rising edge will work just fine. We can model this as to our slope of our sine wave matching up with the square wave. Then we can determine the frequency based off of that sine wave. Okay, so how does that work? Well, sorry, got to jump into a little calculus here because I'm going to derive something. I actually had to pull out a calculus book, which I haven't done 20 years, but it's really important to understand this. In our calculus days, we had derivatives. Derivatives. Why do we even bother with derivatives? Because they gave us the tangent of some type of line. Didn't have to be linear, but some type of line at any given point in time. Okay. So we have a base equation here. It's a sine wave. So again, we're trying to model the sine wave over here from low to high. Okay. And when we take the derivative of that, it comes out to this, 2 pi f cosine, and so on and so forth. So we take this derivative. So what are we going to do with this derivative over here? Just a side note before we go. You may say, well, where's the amplitude? Well, it's not needed because it's defined by it's defined by the digital amplitudes, which would cancel out anyways, because what we're going to do is we're going to take this over here, and we're going to also take the fact that we know that from V1 to V2 over the rise time is equivalent to this. So the amplitudes would drop out anyway. And that's one thing to understand, is that when we model this here, we're trying to model this based off of the same signal amplitudes that we would, so the sine wave is going to be the same amplitudes that we have for our square wave. Okay. At T0, what do we consider to be T0? That is the point of the rise time itself. Okay, the midpoint of the rise time. All this good stuff drops out. We get 2 pi f. In general, we also know the rise time, which is really, okay, from V2 to V1, which is the delta, we get the T rise time. So if we combine these two facts together, here's our equation. Well, guess what? We know the voltage, right? If we look in the data sheets, it will tell us we're going from some voltage low to some voltage high. We also know the rise time. That's going to be in the data sheets as well. All right. From there, we just do a good old-fashioned algebra. We get our frequency. So if you know the voltage levels and the rise time, you're going to get the frequency. You know it. So here's an example that I did here. So for something that's going from 0 to 3 volts and a rise time of 1 nanosecond, we get the result of 477.5 megahertz. So that's step one. We now have a frequency. Well, I need to get a distance over here. Okay. So at what length will turn this into an antenna? That's the big question we need to answer. Well, we also need to have a velocity. So again, I know from a lot of us, if we get into a certain field in electrical engineering, we tend to forget some of these things that we learned back in college over here. But just recall that the velocity is needed in order to get the wavelength in addition to the frequency. The velocity is given by c. C is the speed of light over the square root of the dielectric constant. So for this case here, we're going to use FR4, which is 4.3. So you've got to know your dielectric constant. One of the things that's really interesting about this, it doesn't matter the frequency over here. This equation will remain the same as long as you use this. It's based upon your dielectric constant here. That's going to come out to 144.7 meters per second. Okay, great. So what do we do with that? Well, again, wavelength is velocity over the frequency. we punch out the math, it's going to be 0.3 meters per cycle, or approximately 11.8 inches per cycle. So remember, we're doing this based on the entire sine wave, but I only want a quarter of the sine wave because that's all I'm doing over here is a quarter of the sine wave. So I can divide that by 4. So now I've got 3 inches. Okay, so what this is telling me is that for this frequency that could occur from this rising edge, the minute I start getting towards 2.93 inches over there, I might have an opportunity for an antenna that I didn't intend. Okay. All right, we're not out of the woods yet. Bear with me. I know this slide is kind of intense, and I didn't want to separate these slides because of the fact that all this information needs to stay together. We have to account for the harmonics, which may also couple. So how many harmonics make up the frequency of the signal? Well, generally speaking, the first 9 to 11 harmonics will do that. But for simplicity's sake, let's just assume a magnitude of 10x in frequency. Okay? Yeah, we can do each one of these harmonics. It's going to be a lot of math. But let's just simply say the magnitude is 10x in frequency. So that now changes us from 477 megahertz to 4.8 approximately. I'm sorry, I'm throwing some approximations out here. 4.8 gigahertz harmonic frequencies. The velocity still remains the same. Again, it's frequency independent. We go to our wavelength over here, and really what we're doing is just moving everything over one additional place. So at the end over here, what we're saying is that at 300, approximately 300 mils, or 295 mils, you may experience a significant energy transfer in the form of an antenna. So we've already derived all this stuff for you. The equations are there. And by the way, if you want these slides afterwards, I'm more than happy to provide them to you. We wanted to give you an understanding of how do you determine this distance. There's a very specific way of doing it, or at least through this model. Just 2 other things here. We talked about, everything I talked about was about digital signal. And oh, by the way, one other thought over here. That 295 doesn't mean that the length has to be 295. It's just of the entire length. It's just saying that a segment that's going to run parallel should not exceed 295. You can still break it away or have it, the line go somewhere else away from the aggressor, but that's the maximum that you want to have them run as close as possible to each other before you're going to have some issues. So for the analog stuff, if you're doing analog, parallel segment rule doesn't really mean anything. Why is that? Because analog signals are really sensitive, and we're not talking about parallel lines at this point. We're really talking about shielding something that's very sensitive, because what are we doing with that signal? Well, if it's in the microamps or in the milliamps, and we're putting it through an amplifier, we could have a gain of 1,000. So we really want to make sure that we're shielding those type of traces. More so with RF and microwave, the more complex equations are definitely going to determine length. Okay, so ours was just a very simple model, but there's going to be equations there that you're going to need to do. We're dealing with narrow band, meaning a very specific frequency, as opposed to broadband where we have multiple frequencies, right? Because when we send, again, a signal from point A to point B and it's digital, there's a number of different frequencies that make up that signal, as opposed to narrowband where we are focused on a very specific frequency. And the way I look at RF and microwave anyways is that this is something that's custom, handcrafted, fine-tuned, that in short the designer really knows what they're doing. So, all right, let me show this one here for a minute. Okay, thank you for sitting through that explanation. Hopefully you found that somewhat useful. Here is the parallel, and here's my section for the parallel rule. So I set up 3 traces over here. So we've got B3, B5, B1, and they are all part of their own rule. So I'm going to bring this up here, and let's take a very quick look at the parallel segment constraint. So I created a very specific one here, and you'll notice that there is a violation. So why is this one violating as opposed to this one up here, which it seems like it's longer? And if I double-click on the rule here, just so you can see what the conditions of it are, is that I said I'm going to set this that if it's 10 mils, that I want to have a limit of 100 mils. Okay? The reason why, and I'll page up over here, is if we do a little bit of a measurement. Okay? By the way, for measurements here, you can always do a Control-M. All right? And if your grid isn't working for you, you can always hit the G key, even while you're in the command. You can change it to 1 mil if you need to. I'm going to escape out because I don't need to do it at this point. And if I go from here to here, okay, I now have a distance of 12 mils that's out of the range of this requirement, so it's not testing against this one. Whereas this one over here, again, if I do a Control-M, I want to measure it, go from this point over here to this point, I'm at 6 mils, so it's within the range because I set it to 10 mils. And now this line over here, if we want to find very quickly how much of this segment is 10 mils, you can always double-click on the rules, but unfortunately they don't just simply say X number. They do it based on coordinates here. And yes, I could do it again for Control M. I could basically do that and go from point A to point B. But there's, by the way, a very simple way of doing this. Let me clear this to make sure I can select it. So we'll go to Reports, and I'll go to Measure Selected Objects. Yeah, I'll select it first. Sometimes it will prompt you for it. Sometimes you got to tell it beforehand what you want here. So again, so go to Reports, Selected Objects, and now it's telling me that's measured 0.124 inches, so it's 124 mils. So obviously I set mine to 100, so that's why I'm violating it at this point in time. So that's what this rule is doing. But hopefully you see that whole explanation I just threw at you is very specific to figuring out what would this distance be before we, what would this distance be before we start radiating together, or the aggressor radiating onto the victim. All right, let's get on to a couple of other rules over here. By the way, the explanations on these other rules will not be as intense. So just that parallel segment rule is one that I think is probably one of the most important rules being provided in the high-speed design rules here. I want to make sure everybody understood those. Let's go on over here. Match length rules. This match length rule is a really slick tool. They don't give you any cool graphics for it. But what they're saying is like, look, if you give me a class of nets, and a class of nets can be as many nets as you want, but within this class of nets, each one of these nets need to be of a tolerance of a certain amount. And the way Altium does this, it says, okay, I'm going to take the longest length of the net, and then I'm going to, based on your tolerance, now this is the default one. Normally you'd have this at maybe 5 or 10 mils as opposed to 1,000. But I'm going to take that, and then I'm going to test it against the other ones, and if they aren't matching up, I'm going to flag them. So let me jump back out of this here and show you this example. I'm going to page down so that you can see this here. Okay, what's nice about the match length, though, you have to have some caution to this, is that the match length works from component pin to component pin. So by the way, my pads over here are actually components. So even if I do drop down the via over here, and in the newer versions of Altium, Altium does account for the length of the via that's done based on the layer stack manager. So it will also account for that as well in here as well, in the equation of this. So did I violate anything over here? So let's take a look at the match length rule. So my match length rule, if I double click into it, I'm saying that I have a tolerance of 10 mils. That's fine. Let's see what my violations are here. So you'll notice that as I go through this, okay, it's claiming that I've got an error with this one. And usually it will also show which two of them they're in violation with. So usually it'll take the longer one saying, well, this is not matching up with the longer one. The other ones aren't matching up. So you can see that it's always doing it in reference to this one here. And then it's also matching up with this over here. So my differential pair has an issue. My original one over here, this one seems to match up just fine, so I'm not having any issues with it. Now, if you use the match length tool, there's also a feature in Altium, and it was a little fussy today, but let's see if we can get it to work very quickly, is that there is, under the tools, there is the interactive length tuning, which is for single lines, and there's also differential pair for the differential pairs as well. So depending on whether you're doing this for the single or the differential pair, and if you click on it, it's going to ask you, well, what do you want to try to match length tune? Okay, so I'm going to choose an object, and as I go along, and it's now good, it's working today, what I can do is I can hit the tab key, okay, not completely working, but I can determine whether I want to just set a target length or if I want to use one from the rules. And for some reason, it's complaining about my rule with the differential pair, and I don't know why it's doing that, but nevertheless, it will. It seems like it's adhering to it, so I'll leave well enough alone. So no, it's actually going off and creating them as I see fit. But if the rule was there, it would try to make sure that whatever I had on C7 and C8 will adhere to, or C9 and C10 will adhere to what's on C7 and C8. So, but that's the idea behind the match length tool. All right, let me jump back over here to our slides. Go back to the current slide here. All right. And go to current slide. There we go. That's what I'll say about that one. Daisy chain stub length. Interesting creature. What do we have to say about this? This is something that was probably used many years ago and probably still used by some people today. But it was to handle branches off the main trunk of a signal, like a clock, or maybe off of a bus. And I'll see it's kind of a semi-archaic way of handling stubs at this point in design. Certainly with DDR3, you wouldn't want one of these type of things. So just be aware of it. The max length stub over here, they basically say, look, if you want to have this over here, this is the max length you allow the stub. There's some requirements for this. Number one, you have to have a pad or a via connected to this. It won't work if you just simply draw a trace or an arc. And you must declare a topology. So there's actually a topology rule, not in the high-speed rules, it's under routing. You have to create a routing topology, and you have to declare it as some type of daisy chain. And Altium actually has different types of daisy chains, but as long as you declare it as one of the 3 different daisy chains, it will enable the rule. Okay. If you do have these stubs, then that's probably because you're using a certain type of bus that's going to require this. However, what we see more often than not, and I think a lot of people who look at this, is they may be looking at this as a test point. So I'm not looking at this at a bus point of view. I'm looking at this as a test point of view. Okay? And the test point of view is this, that a lot of times people want to have something so they can put a probe on it and see how that signal is behaving. The problem with this is that if this is not connected to something, you basically have an antenna. Right? And if you have an antenna, you guarantee a reflection, or a stub, you guarantee a reflection, unless you purposely understand how you're doing this and how you're terminating this. And if you're changing the trace width here, and that's exactly what you're doing, if you're basically going along and you instantly change the width, you have changed the impedance. And really, quite frankly, when it comes to test points, again, only test points, there may be types of buses that handle these stubs rather well, but from a test point of view, length has nothing to do with impedance. So you don't, the only time this might be of any type of use to you is to make sure that if you go too far out, for example, on a regular signal, let's say not a test point, but on a regular signal, all that stuff we talked about the parallel length would still also be applicable to this, where you don't want an accidental antenna, but that's again assuming that this is actually going to some component and that you're trying to build a bus topography that way. But from a test point of view, this is really not applicable, because no matter what your length stub out is over here, you're going to have some type of reflection. That's what you want to avoid. Again, I want to go back to the fact that impedances are defined by the width of the trace, the height of the trace, and the dielectric constant of this, in addition to the distance between the trace and the plane itself, not defined by distance. Okay? Daisy chain stub length, if we go over here, if you really need to have a test point, therefore, the easiest way to handle this is to actually put the test point right onto the signal itself. Yes, if this is wider over here, you are going to get some type of reflection, or you're going to change the impedance a little bit. However, if this is kept small enough, and given the fact that the material is still pretty much the same material, you're not going to a completely different material, you'll find that these gammas over here are small enough where they may either be minuscule, so have almost no impact, or no impact in particular, because they're going to just cancel each other out. So just kind of keep that in mind. If you really need to put a test point over there, just be aware of that. All right, the 5th rule, V is under surface mount pads. What are they trying to address here? High density boards. It's kind of weird, because you can, as long as any 2 copper primitives exist in Altium and they've got the same net name, it's going to allow this to work. Okay? So you can set this up if you want. I think really what I want to talk more about than anything else is the implication of putting a via underneath an SMD pad, because this is really important. So if you have something that's very high density and you can't dog bone this out, then you may want to consider this. So this is a classic way of handling any type of ball grid array. I've zoomed into just a handful of them over here. This is where your solder ball of your ball grid array would sit. It would go through a small little trace, and then you've got these, you got this via over here. So that's why they call it a dog bone. Okay? Now, the problem that you get into is some of these packages are so densely packed, they don't even give you enough room to put the dog bone in, or the solder mask over here is so thin that it will actually pull away. It could get stuck somewhere else and cause problems in the assembly. So if you can't do that, then if you can just imagine, forget about this part of the dog bone, what you've got over here is that you've got a through hole, or basically you've got a pad with a through hole via on it, and that will solve at least your problems for the immediate term. However, there are huge implications to that in the fabrication side of stuff. So if you decide that you're going to do what they call a pad in via, okay, or pad on via, you have to do a couple of things over here. First and foremost, you've got to understand that you've impacted your fabrication. There will be more cost associated with it. And number 2, Altium doesn't really have a mechanism that says, if I've declared this to be a pad in via, because there's really nothing in there that says you can declare a pad in via, you are going to have to draw up some type of application note or some type of diagram saying the following components or the following pads have to be filled in. And so here's the extra process that you got to go through. Because if you basically, in the assembly process, if you take a ball grid array and you simply put it where my cursor is, we'll take number 2, which is the plate through, and then you put it through the process of heating up that solder, the solder is just going to wick right through, and it's not going to make any connectivity. So you got to stop that wicking from happening. So what you got to do is you got to plug it, you got to harden it, you got to polish it, all these other things, so that in the end, yes, you do have that connectivity that goes through the board, but you also now have a situation so that the solder doesn't run through the board. Instead, it just sits there, and it now allows connectivity between the board and the component itself. So be very aware of this. It's a great technique, and it's a great technique. Definitely be aware of it, but also understand from the start that if you're going to go down this path, there will be more cost associated with your printed circuit board. All right, last one over here is this one called max via count. And the max via count is an interesting creature because some people, and it's not some people, it's myself as well, there's a lot of misnomers and misconceptions about vias. Now, in the old days, the more vias that you had, and I think some certain fabricators still adhere to this, the more you had, if you hit a certain limit, they would charge you extra for those hits with the drill, because maybe they got to switch out the drill after so many hits and they wanted you to take on the tooling cost of that. So that's why they have this over here. Quite frankly, I think this is really more of a rule for for fabrication than I think for high speed. So the question is it too many vias, not enough vias? What kind of gives over here? So obviously there's more cost if you've got more vias in there. And the interesting part is in high-speed design, we want as many vias as possible. Where? We want them on the planes because we want as much connectivity between the planes and different layers as much as possible. So when and why do we use them? Can we use them on signals? The answer is they're best to avoid, however you can use them. And a lot of people are like, are you kidding me? In high-speed design, you're going to use a via? No way. Well, yeah, way you can use them. You've got to keep in mind, it goes back to the thing we talked about at the very, very beginning. And what's this at the very beginning was that we have a current loop. Yes, if you've got a signal that's going through a via, you're certainly going to get propagation delay issues because there's an LRC associated with it because you have a different impedance. So there's no doubt that that does exist. Okay, but that's not the reason why people have problems with it. The reason why individuals have problems with it when they're drawing these things, again, we have that point A to point B concept. In our heads, we forget about the point B to point A concept. So what we can do over here is that if we are, for example, going from layer 1 down to layer 3, okay, and we have a reference plane of layer 2, one of the things we can mitigate for that signal via is to make sure that we put a return via that attaches the ground planes that are associated with that signal on whichever layers you've got over here. So when you're working with these things, if you've got to use a via to go from one layer to another, then as long as in the back of your mind you said, okay, I need to get this signal back to point A, and I got to put some type of secondary signal that can ensure that through a via, that's going to work. So as long as you understand the current loop over here, you can mitigate a lot of the noise that you're going to get in a via. But yes, if you can avoid a via altogether, all the better. Sometimes you can't, but that doesn't mean the death of your high-speed design. So with that, I will show you one other thing here, and then I know I'm really pushing for time, and I know that your time is precious. Let me do a view fit here. These rules are very straightforward. I do want to show something over here with the max via count. More than anything else, I want to show the new feature that Altium provided, which is called the X signal. Okay? So the X signal itself, I already created one here, and then I'll show you how to create one. The X signal I already have over here, if I click on it, you'll see that I can do with now the X signals, I can go over here. As opposed to prior to Altium Designer 15, if I was going to split this off for whatever reason, again, be careful when you do these things because you're going to have big impedance impacts on stuff. You better know what you're doing with it. But if I wanted to do something where I do want to split these things off, in the past I would have had to create some kind of dummy component. So Altium would have looked from F3 to this point, and then from that point to F4, or this point to F5. With the X signals, not only can I do that, I can also jump over. So if I have a series resistance, I can go, let's say there's an F6 over here, but there was a series resistance between F4 to F6. I could actually create an X signal from F3 to X6. So how do I, and if I create this over here, you'll see that it now exists, and so it'll show me all the pads that are, or traces that are associated with this. Okay, how did I create it? It all starts, there's two different ways you can do it. You can either do design X signals here and say create X signals. And what it needs to know is where's your source component and where's your destination component. And this is really important because Altium can't just take a segment over here and declare it as an X signal. It does have to start on some component pad and it's got to end on a component pad. So for example, if I did want one from literally F3 to F4 and to ignore F5, I could go over here and let's take this over here. So I'll say I want to go from F3, so I'll click on this one, and now it needs to have a source, so F4, okay, I'll go over here, pardon me, destination, okay, and it'll analyze these two since I've selected them, and it'll see, okay, what do we need to do this? So I'll say search for direct connections, it does find it, okay, so it's going to go from F3 to F4, and I can press OK, and it'll now add that into my X signals. You can also do this, by the way, in the nets as well. You can click on each of the individual components, on each of the individual pads. You can right-click once you've got two of the pads connected. You can right-click on it and say, okay, I want these two to match up. Once you've got this over here, you can actually create a rule here. And the reason I did this is just to show what happens here with this rule. So what I did was I created a rule that says that I don't want, if I have four or more pads between these two, between point A to point B, then I want you to flag it as an error, and that's what it does. So let me grab, let me see if I can find it. I was having a little bit of an issue finding this one a little bit earlier on, but hopefully we can find it here. So it's either going to be max via or via under maximum via count constraint. So here it is. And you'll notice over here that I set up this rule. Let me double click on it so you can show it. So when you create a new X signal, it gives it its own special name. And I told it, hey, look, I want a maximum via count as 1. Well, there's no error or violation over here because you can see that it does not entail any of the 4 vias I had on the other part of this segment, right? As opposed to this one over here where I go from F1 to F2, and this violates because I said I had a maximum count of 2, and there's 3 over here. Now, if I set up another rule, for example, between F3 and F4, I would violate it unless I change the rule to be more than 4 vias at this point. I know I'm at the end of my hour over here, and I know I've thrown a tremendous amount at you. I do want to remind you that if you're interested in this webinar, because you want to review it again, we will make it available very soon. So if you want to contact any of our, contact our representatives or use our website to contact us, feel free to do so. We'll make this available to you. We will definitely make this file available to you as well so you can see what I did to set up these rules, because that may be useful to you if you're trying to get your head wrapped around the rules a little bit more. And we'll also make the PowerPoint available, we'll do it in a PDF form, so that if you want to see this equation that I just spent a good portion of time talking about, you can see how we derived it and you can make use of it as well. I may have time for 1 or 2 questions, and then after that I'll let you guys go because I know that you're very, very busy and I know I'm past the hour. So it actually looks like at this point in time I don't have any questions, and if you still do, feel free to send them. I will grab them. I think that my assistant here has been wonderful in answering some of these questions as they've been coming in, as they've been going, so I don't think there's anything outstanding. So with that, I really want to thank you very much for your time, and let me just draw up my other slide over here, and take care, and we'll see you next month.